So today we are talking about the ratio test for infinite series. If you have a series that is a positive term series and you calculate the ratio of the next term to the previous term and take its limit as n approaches infinity, if the limit is less than 1, the series converges. If the limit is greater than 1, the series diverges. And if the limit is equal to 1, the ratio test is inconclusive and you need to apply a different test. This is a test that is particularly useful for series whose functions involve factorial or series whose functions involve exponential functions, which I will do some examples and demonstrate. Sometimes you'll see the ratio test stated like this. Instead of explicitly stating that a condition is that the terms of the series are positive, it will be stated that the limit as n approaches infinity of the absolute value of the ratio of the next term to the previous term. So that means the same thing. All right. So first, I'm just going to do two examples, use the ratio test on two examples to show that when you get a limit that is equal to 1, the ratio test is inconclusive. So this first series is a p series. It's a special p series where p equals 1. So we have 1 over n. Again, like I said, this is a p series. P equals 1, which is less than or equal to 1. Therefore, this series is divergent. So if I do the ratio test on this series, which this is a positive term series, if I take the limit as n approaches infinity of a sub n plus 1 over a sub n, I'm going to get the limit as n approaches infinity of a sub n plus 1 is 1 over n plus 1. And if I divide by 1 over n, which is the same thing as multiplying by n over 1, I get the limit as n approaches infinity of n over n plus 1, dividing by the highest power of n in the denominator, that's 1 over 1 plus 1 over n, which equals 1 over 1 plus 0, or 1 when I apply the limit. Okay, here's another p series. So this is the sum from n equals 1 to infinity of 1 over n squared. So like I said, another p series. P is 2, which is greater than 1. Therefore, this series is convergent. Okay, now if I do the ratio test, this is also a positive term series, a condition necessary to do the ratio test. I'm going to have the limit as n approaches infinity of a sub n plus 1 over a sub n, which is the limit as n approaches infinity of this. Okay, so again, the limit as a sub n plus 1 over a sub n is the limit as n approaches infinity of 1 over n plus 1 squared divided by 1 over n squared becomes times n squared over 1. This is the limit as n approaches infinity of n over n plus 1 quantity squared, which is the limit as n approaches infinity of, if I divide by the highest power of n in the denominator, I get 1 over 1 plus 1 over n, which is 1 over 1 plus 0 quantity squared, or 1. So here I have two series, both positive term series. I'll write that up here just to remind you that that is a necessary condition. And I've showed you that one of these series is divergent and one of these series is convergent using the p-series test, and yet using the ratio test they both have limits of 1, which shows that the ratio test is inconclusive when the limit of the a sub n plus 1 term over the a sub n term equals 1. So now we're going to do some examples to show how the ratio test works. Okay, we are going to use the ratio test to determine the convergence or divergence of this series. And I know that this is going to be a good candidate for the ratio test because I see the factorial there. First, I'm going to just confirm that this is a positive term series, which is the condition necessary to apply the ratio test. Okay. So I'm going to take the limit as n approaches infinity of a sub n plus 1 over a sub n, which is the limit as n approaches infinity of, this is going to be 3 to the n plus 1 over n plus 1 factorial divided by 3 to the n over n factorial. Now I'm going to get rid of the complex fraction by multiplying by the reciprocal of the denominator, 3 to the n plus 1 over n plus 1 factorial times n factorial over 3 to the n. Okay, now let's go ahead and simplify this. So n factorial over n plus 1 factorial, that's going to simplify to 1 over n plus 1. If you think about, if you have 5 factorial over 6 factorial, the numerator is 1 times 2 times 3 times 4 times 5. The denominator is 1 times 2 times 3 times 4 times 5 times 6. And you would be left with just 1 over 6. And then here I have 3 to the n plus 1 divided by 3 to the n. That's going to leave me with a 3 in the numerator. Okay, so simplified, I get the limit as n approaches infinity of 3 over n plus 1. So I am going to evaluate my limit now. Divide by the highest power of n in the denominator, which is n to the first. And I'm going to get 0 over 1 plus 0, which is 0. And so 0 is less than 1. If the limit as n approaches infinity of a sub n plus 1 over a sub n is less than 1, then our series diverges by the ratio test. Okay. All right, so here we have our second example, the sum from 1 to infinity of 3 to the n over n squared. This is a positive term series. For all n, or as long as n is not 0, but we are only concerned with n from 1 to infinity. So I am ready to do the ratio test. I'm going to take the limit as n approaches infinity of a sub n plus 1 over a sub n, which is the limit as n approaches infinity of 3 to the n plus 1 over n plus 1 squared divided by 3 to the n over n squared. Okay, let's rewrite that and get rid of the complex fraction by multiplying by the reciprocal of the denominator. So I'm going to multiply by n squared over 3 to the n. And then this 3 to the n plus 1 over 3 to the n, that is going to simplify to just a 3 in the numerator. And the n terms, well, the n terms I can combine into a single fraction raised to the second power. So I'm going to write that as n over n plus 1 quantity squared. And so now I have 3 times the limit as n approaches infinity of n over n plus 1 squared. To evaluate that limit, I'm going to divide by the highest power of n in the denominator. And I'm going to get 3 times 1 over 1 plus 0 squared. All right, so 3 times 1 over 1 plus 0 squared, or just 3 times 1 squared, and I get that the limit of the ratio of the n plus first term over the nth term as n approaches infinity equals 3, which is greater than 1. And therefore, my infinite series from 1 to infinity of 3 to the n over n squared diverges by the ratio test. Okay, so let's look at our third example, the sum from 1 to infinity of n to the n over n factorial. We've got a function, exponential and factorial in our function, so I know this is a good candidate for the ratio test. This is a positive term series. As long as n is greater than or equal to 1. Okay, so here we go. The limit as n approaches infinity of a sub n plus 1 over a sub n is going to be the limit as n approaches infinity of n plus 1 to the n plus 1 over n plus 1 factorial divided by n to the n over n factorial. Now I'm going to get rid of the complex fraction by multiplying by the reciprocal of the denominator. N plus 1 to the n, n plus 1, there we go, to the n plus 1 over n plus 1 factorial times n factorial over n to the n. Okay, so again, I have this n factorial over n plus 1 factorial, and as I stated earlier, n factorial over n plus 1 factorial is going to reduce to 1 over n plus 1. Then I'm going to take a step and I'm going to rewrite n plus 1 to the n plus 1 as n plus 1 to the first and n plus 1 to the n. Okay, so let's make those changes. That gives me the limit as n approaches infinity. So my factorials, n factorial over n plus 1 factorial, as we said, simplifies to 1 over n plus 1. Then in the numerator there, I have n plus 1 to the n, n plus 1 to the first, and then in the denominator, I still have an n to the n. Well, now you can see that that's useful because these n plus 1s are going to cancel out. And now I'm left with the limit as n approaches infinity of n plus 1 over n to the n. And another way, I'm going to get an indeterminate form, but another way I could write this is the limit as n approaches infinity of 1 plus 1 over n to the n. And now you can more easily see that when I plug in infinity, when I actually take the limit, I'm going to get 1 plus 0 to the infinity. And as we learned earlier in the year, 1 to the infinity is an indeterminate form. And I am going to use the method for indeterminate forms to solve that. So let's skip to that. Okay, so here we are with this expression here. I'm going to start right here. Okay, so let's let y equal 1 plus 1 over n to the n. Then the natural log of y will equal the natural log of 1 plus 1 over n to the n. Or the natural log of y will equal n times the natural log of 1 plus 1 over n. And we are going to find the limit as n approaches infinity of the natural log of y. Okay, so this is going to be the limit as n approaches infinity of, what do we have here? The natural log of y is, sorry, what's going on here? I think I'm going to need some more room. So I'm going to start this on a fresh page here. So let's go to a fresh page. Okay. Okay, so here we have, let's start here. So this is going to be the limit as n approaches infinity of n times the natural log of 1 plus 1 over n. So this is, we're going to put this in a form that allows us to use L'Hopital's rule. I can rewrite this as the limit as n approaches infinity of the natural log of 1 plus 1 over n over 1 over n. And now when you evaluate the limit, you get the natural log of 1 plus 0 over 1 over infinity, and this is 0 over 0. So now I'm going to apply L'Hopital's rule, and again, I'm applying L'Hopital's rule to this limit, and I'm going to get the limit as n approaches infinity. Okay, in the numerator, I'm going to get 1 over 1 plus 1 over n times the derivative of 1 plus 1 over n, which is 0 times negative n to the negative 2. And then I'm going to take the derivative of the denominator, and the denominator is also going to give me a negative n to the negative 2. Getting rid of the complex fraction, I have negative n to the negative 2 over 1 plus 1 over n times 1 over negative n to the negative 2. I can then cancel those out. That's gone. And I'm left with the limit as n approaches infinity of 1 over 1 plus 1 over n, which is going to be 1 over 1 plus 0 or 1. Okay, so let's go back. We decided to take the limit of the natural log of y. And what's the reasoning behind that? Why is that helpful? So from that, we can say if the limit as n approaches infinity of the natural log of y equals the natural log of the limit as n approaches infinity of y, which equals our answer, then by changing this expression into exponential form, we get that the limit as n approaches infinity of y is e to the 1. So what was our goal here? It was the limit as n approaches infinity of y, and y was 1 plus 1 over n to the n, equals e. So let's go back to where this work started on the previous slide. And basically, we did all of this work here, and we came to the conclusion that our limit, which again, this goes all the way back to here. The limit as n approaches infinity of a sub n plus 1 over a sub n winds up being e, which is greater than 1. And therefore, we can conclude that the sum from 1 to infinity of n to the n over n factorial diverges by the ratio test. All right, we have our fourth example here. The sum from 1 to infinity of n to the 8th plus 8 over n factorial. So this is a positive term series. For n is greater than or equal to 1. And so I'm going to take the limit as n approaches infinity of a sub n plus 1 over a sub n, which is the limit as n approaches infinity of n plus 1 to the 8th plus 8 over n plus 1 factorial. And then dividing by a sub n is multiplying by the reciprocal of a sub n. So this is going to be n factorial over n to the 8th plus 8. Okay, so again, I have this ratio of n factorial over n plus 1 factorial, and we've seen several times that n factorial over n plus 1 factorial is going to reduce to 1 over n plus 1. So I am going to have, after I simplify that, the limit as n approaches infinity of n plus 1 to the 8th plus 8 over n plus 1 n to the 8th plus 8. So now you can see I'm taking the limit of a rational function, and the expressions in both the numerator and the denominator are polynomials. Now, I don't actually need to do all of the multiplication, but I know that if I multiply out the numerator, I'm going to get a polynomial whose leading term is n to the 8th. Okay? And then if I multiply out the denominator, I'm going to get n to the ninth, well, this I could multiply out more easily, plus n to the eighth plus 8n plus 8. It doesn't really matter what all of the terms are after the leading term, because remember that the leading term will determine the answer, the value of this limit. Again, you would divide by the highest power of n in the denominator, which is n to the ninth. And so every term in the numerator would be some fraction with n in the denominator. Whereas in the denominator, I'm going to get 1 plus several terms with n in the denominator. So I will wind up with 0 in the numerator, many zeros, 0 plus 0, etc. And in the denominator, I will wind up with 1 plus 0 plus 0 plus 0, which is 0 over 1, or 0. So 0 is less than 1. The value of the limit of the ratio of the next term to the previous term as n approaches infinity is less than 1. Therefore, this is convergent. Or actually, let me be a little more specific here. My series, the sum from 1 to infinity of n to the eighth plus 8 over n factorial, converges by the ratio test.